Jacques Carette from McMaster University, who will tell us how to integrate definitely properly. Oh, sorry, we're going to be taking Jacques out for dinner at 6:50. Sorry. 6:50 p.m. tonight at Spices Inn. Something like this. And 371 George Street. If you'd like to join us, please let me know immediately after the talk.
Right. So today we're going to really take a look again at just definite integrals, very simple ones. And if you, most people will get taught Riemann integration, and I'll review that. But over the years, there was various, let's do this, and then Lebesgue, then Daniel integral, and then Henstock. Kurzweil integral. So each one of these are more and more and more general, and this is as general as we get. They're quite fast. So this is also called generalized Riemann, or more interestingly, the gauge integral. The interesting thing about the progression of these more and more general integrals is that they integrate less and less continuous functions. In fact, things that are less and less like functions, because they only need to be defined on a set of measure zero. In fact, they don't need to have values anywhere. They can be funny things that are really far from functions, because they don't have values, because when you're up to measure zero, you can change any value you want, so you can't actually evaluate it anywhere. And my motivation really is to let's call it integrate formulas. I come from a computer algebra background, and I'm really interested in formulas or functions that you can name and evaluate. Those are the ones that I'm really interested in. And I'm interested in the nice ones. What can you do with the nice functions that you can name? Those are the good ones, functions that I can name. And the Henstock-Kurzweil integral does not help me any more than the Riemann integral to integrate functions that I can name. They've got exactly the same power for integrating functions that I can name. And I find this annoying, because there's functions that I can name that cannot be integrated. And yet, really? So of course, at this point, you always want an example. The most obvious. And he says, no, that diverges, that goes to infinity, that's no good. But we should have learned by a whole lot of mathematics by now, that divergence is really not that big a deal. As long as you don't diverge too fast, it's okay. Don't worry about it. This is very slow divergence. It should be okay. So we want to tame this and go, let's see what we can do with this. That's not so bad. Right. Another disease that classical integration has is so integral is it linear? So yeah, kind of. If this is defined and that is defined and this is defined and they're equal. Great. If we have two things we can integrate and we know the answer, we can put them together, and so it's compositional. Great. Now, we're interested in computation. Typically, in a computation, you have an integration problem, and you stare at it, and you have formulas, and look, it's a sum. Great. We can decompose, split it up. We can go this way. No, we can't. The theorem says, no, 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 you can go that way. That's perfectly good. You cannot go that way. The only way you can go that way is if you make sure that both of these are integrable. And then it's okay to go that way. Well, that's kind of annoying. Because sometimes I'd like to split off a piece. So if I have something as simple as, you know, great, you know, but, you know, I'm integrating that. And it's all messy. And I say, oh, well, actually, you know, split this off from this, split it out, and then magically I know the answer to both. Well, no, you don't. You can't, because you're trying to do this. And the theorems say, no, don't try to do that. And no matter how powerful your integral is, it still won't help you. Okay. So it'd be nice to try and fix that. Now, we can't fix that completely. That would be hoping for too much. But we can fix it to a certain extent, so that some singularities are not a big deal anymore. Right. So to really kind of look at how it works, we really need to go back to the definition. So we have a tagged partition is, just want to make sure I keep the same notation for x naught, then t naught. So we're looking at integrating from a to b f of x dx. And so what we're going to do is we're going to split up at, so we've got x0 here, x1, x2, and so on. And so we split it up into normal partition. And in each one of these partitions, we label a particular point. That's all a tag partition is. And then basically, if delta I is xi plus 1 minus xi, it's probably the other way around, and yep, of course. So if delta I is the width of one of these, then we're interested in the sum from 0 to, just want to make sure, n minus 1, f of pi delta I. So basically, all we're doing, this is back to first year calculus. We're picking a point and we're integrating nice rectangles, and we say, that's the process that we're interested in over here. And if we make the right definitions, that's eventually going to converge to an integral. So we want to say the mesh of a tag partition is the max over all I of the width. So the mesh width. So we're interested. How big are the pieces in our partition? We call it delta fine if the mesh width is less or equal to delta. And so now we get to the actual definition of, I think I'll do it this way. Oh, I guess I need to push that up. Push up? All right, well, I guess I'll keep traveling. Or, no, not so much.
Yeah, you should have started here, sorry.
Sorry?
You should have started with this one.
Yes,
Yeah,
but
thanks.
I didn't think of it. So then we basically say that the Riemann integral, we say that fx dx is S if there exists a delta fine partition such that for all epsilon greater than 0, we have integral if this delta fine partition such that S minus the sum is less than epsilon. So basically, if you look, whenever you're trying to approximate, you say, okay, I want to get close enough. This is my approximation. This is how close I want to get to it. There must be some delta where no matter which partition, actually, for all delta fine partitions, so there exists a delta greater than 0 such that for all delta fine partitions. So that's the official definition. We need to be close enough to the approximation. That's just a reminder of definition. By the just a very minor variation of that actually gives us the Kurzweil-Hinstock integral, but I don't think I won't go into that. So what we really want to do is to start staring at this definition and move things around a little bit to see what can help. And one of the clues to what's going to be going on here is that there's a summation process here. So we're actually approximating our integral. There's actually a process by which we're going to our integral. So we want to dig out that process and want to see how does that process work. Right now, all we're saying is we can make it close to S. Well, how does it go to S? And that's what we're interested in. This is what is going to work for us. So logic helps us. First thing we do is scolarize this. This there exists here. It's kind of annoying. It's not very constructive. So we get for all g real to real functions, for all epsilon greater than 0. I won't repeat everything. Basically, we get a G epsilon fine partition S minus same thing. Okay, so this might look like it's wrong because I've taken this delta and I pull it out here, which I can do, but now I have this G that works for everything. This is wrong. That's because really this for all, you should see this as having a lambda f, a, and b out here. So I take as input a function and two inputs. And then I have this. So my delta kind of depends on all of this stuff, because it's way in. When I scolomize, actually this G here also depends on F, A, and B. So, yes?
Do you mean for all G or exist G?
You're absolutely right. Exists G. I've pulled out. Is this right? So I've got an existential inside that's no good. I want it on the outside because it makes my life nicer. Thank you. Thank you. Going too fast. So we get this function that if we want to approximate to scale delta, to level epsilon, then this function is going to tell us, given an f and a and a b, how much. So this is no different than delta here. This is just saying, oh, I'm going to give an explicit function that gives me delta. Right. Well, it's pretty natural to say that if you want a finer approximation, that's going to mean you're going to have a finer partition. So let's assume that that's the case. There might be steps. It might jump, but we can assume it's monotone. So I'm going to skip over the details here, but basically there is an inverse function. You can invert it because the approximation is monotone. So if we rewrite this again, is this here, we call this delta, and this epsilon here,
G inverse of delta?
it's G inverse of delta. Yes. It's all correct in my notes, and now I'm trying to remember it. So this G epsilon is delta. So this epsilon is G inverse of delta. Okay. So now we can forget about epsilon. And what we have is that so at scale delta, we get an approximation at G inverse delta. So what we've done now is simply interchange the role of how close we want to approximate to at what scale are we looking at things. So this is now going to be the main variable. I'm going to look at the scale at which I want to look at things, and this is going to give me a certain degree of approximation. And what this basically says over here is that normally is roughly, and then I'll write it this way. Basically, normally what you're interested in is that the summation process gives you the answer plus an error. But now we can actually say that error is actually a very specific function of the scale. Right. So that's our integration process. This is the thing that we're interested in. And it's asymptotically as we look at a finer and finer scale, equal to our answer plus something. Well, why do we care that it's actually a constant plus some other function in delta? Let's forget the shape and just look at it as some function h of delta. And in fact, one of the things that is going to free us is, well, we want h's that have an asymptotic development at 0, is what the ones that are really interested in. But we don't actually care that they are convergent. If this process diverges at a particular speed, we would like to measure that speed. So if this process diverges nicely with respect to delta, and we can measure it in this h that we get, we're happy. Because we're trying to integrate something, and we get an answer that says, no, it's not a classical answer because it diverges. But here's the speed at which the process diverges. So maybe this is useful. This may allow us to proceed further and integrate some formulas that otherwise can't. We've got to be careful not to call it the integral. It's an approximation. It just tells us the speed at which this process, what does this process do? And if you're interested in its behavior as you refine the scale delta, that's exactly what it gives you. It doesn't give you any more than that. Right. So, yeah, I'm going to start using the laptop really soon to actually show some examples. Just the screen needed. What I'm going to do is do some explicit computations with some specific summation processes. So the thing I'm going to do is this tag partition with its width, that is a particular summation process. We can replace it by other. That's not the only summation process that works, as long as we have something that approximates a classical integral. That's going to be what we want to look at. Right, so I'm going to be using Maple, and so I've got a delta that's small. The rest doesn't really matter for now. Let's start. So let's start with really, really simple things. I'll try to integrate x. So the process is supposed to be here. Anyways, the process, as simple as possible here, is the rectangular rule for integration. I'm going to integrate at every delta, and then how many steps do I have? Well, it's this nasty thing. So if I actually, well, I should run the whole thing. So if I start from something as simple as x, I get from a to b, I get something quite nasty but that's exactly what is going on. You're approximating and you're getting this great big mess, and if you at the next one it'll be simpler to see what's going on. What I'm going to do is I'm actually going to try and figure out as a series, how does that work in delta? Now the floor of b minus a over delta, that's kind of ugly. So I'm going to say, well, actually, let's look at it as b minus a over delta plus the fractional part of that. The fractional part is something between 0 and 1. So some constant c. I'll just throw that in and